Welcome back to another HVAC-Engineering-Techie training video. Today's lesson is on how to select and size control dampers. Control dampers are a little simpler than control valves, but still have some of the common attributes. So today we'll go through that. Remember, this is the Techie channel that talks all things HVAC, from design, clear efficiency, performance, and everything in between. So I'd like to ask you a favor. I'd like you to become a subscribing member if you would. If you already have, thank you very much. I appreciate that. It's really easy to do. You just hit the subscribe button down below. Give me a thumbs up if you like the video. Those are free, cost you nothing, it's painless. You just click on it, put in your email address, and you're subscribed, and then you'll see all the videos as I produce them. It doesn't cost you anything, but what it does for me, it's really helpful because Google uses that data to evaluate my videos, which keeps me on the air. So if you do that, I really appreciate that. Other than that, share the videos with your friends and coworkers, as they might need the same thing that you're looking at. Appreciate it. Let's get started. Let's take a look at control dampers. So before we start on control dampers, I'm just going to go through the list of videos for controls. I know you've probably already seen this, but if not, these are the ones that are available to help you. C1 is HVAC control basics. C2 is DDC controllers and network devices. C3 is DDC control architecture, the layouts and the networks. C4 is DDC control components and devices. C5 is DDC control installation and wiring. C6 is water central plant control system sequences. C7 is hot water central plant system sequences. C8 is chill water plant control system sequences. C9 is constant volume air handler control system sequences. C10 is VAV air handler control system sequences. C11 is outside air handler control system sequences. C12 is tuning DDC control loops. C13 is how to select and size control valves. C14, which is this video, is how to select and size control dampers. And C15 is HVAC pneumatic controls. So these are the different videos you can see. All these sequence ones delve real heavy into the reset sequences, because that's where we've had a lot of trouble in our industry. So these are using guideline 36 to kind of clear up some of that confusion. I hope that helps. All right, let's look at control damper types. There are two types of control, actually three types of control dampers. The first one is called opposed blade, and that's where the blades are opposed and they go opposite direction. This one opens that way and this one opens that way. And what they have is they create a jet right between here. As they close, it gets smaller and smaller and smaller, creates a jet. So opposed blade dampers provide straighter airflow and provide a mechanical advantage for the distribution of pressure against the blades, allowing operation with a lower torque actuator. So you can tell as if the air is coming this way, as this blade closes, this is causing pressure because it's trying to back up this pressure. But at the same time, as this closes, it's pushing against this one, which is helping it close. So you get kind of a pressure here, your pressure force this direction, and a pressure force this direction. So that's why an OPD takes a slightly smaller actuator than a parallel blade. This is a parallel blade. And of course in it, the blades are the same. It's just that the blades are all moved the same direction. So as this opens, this one opens, this one opens. So parallel blade dampers provide airflow in one direction and have a higher closure pressure requirement and a higher torque actuator. So what happens is this one closes, and OBD it creates jets. So that you get this high stream jets going through here. And here at the edges, this one, the air, it actually forces the air down. So you're actually directing the air in a direction. This one is just straight, but it's jet velocity. This one is directing the air down as it closes. And that helps sometimes if you're trying to mix air a certain direction. You can use a parallel blade a little more effective. Now, to tell you the truth, both these have almost the same characteristics except for what I just explained. So there's no real advantage over one over the other, except this one can direct flow in a certain direction. I know that a lot of people argue that this is a better damper, this is a better damper, but in truth, they both do the same job. They both use almost the same energy. This uses a little less, but in reality, they don't. And the third kind is a round damper, and a round damper is a control damper used in many applications, which is more like this damper than this damper. So it is a round damper. Now, some people have actually make an OBD for a round duct, but it's actually a square OBD with just round duct fittings. Okay, control damper types. Now, this is the actuator types on this. This is a non-fails two position. And this one, normally it doesn't have a wire here. It showed that here. And as this controller, this is the black wire. This is the actuator. And remember that in electronics, black is common and white or red is positive. It's just opposite of power wiring, so you got to remember that. So as this actuator clicks on the point, this is a motorized actuator, and it begins to open the actuator. And most of these are designed so that when they're not opening, they are closing. So with the spring return, and this will actually close it if it's spring return. It can also be electric return. And in this position, if at that point it's electric return, this electric would actually close it. So it's either this one or this one. And that's a two-position actuator. Here's a two-position floating position. It looks almost like this, except it has a center point, and this has a different controller output. Takes 2 points, of course, but this still has the common, and the red will open the actuator, and the white will close the actuator. But what happens is it can stop in between. So let's say you have it's on a damper, and you want the damper to open, so it starts to open. This closes, so it starts to open, but then it stops because it no longer needs to open. It's at the right spot. It will stop, and it will stay at that spot. And then if you go a little further, you need to open some more, it can close that point again, and then it will start to open a little bit further. And then if it wants to stop, it will stop. And then if it needs to close, it'll close that point, and it'll start to close. So this mimics modulation because it'll go along, go up, go down, go up, go down, and it mimics modulation. It's not as good as modulation, but it's close. And this is a safe modulating actuator. Here's the actuator. See the common up here and the red? So it's got a power to the motor, and then it's got control components inside this actuator. And this is a analog output. So it's got a positive signal and a common signal, a negative signal. And it sends either 2 to 10 volts or 4 to 20 milliamp, depending on the type of actuator. And what it does is it says, okay, I need to be at 50%, so it sends out 6 volts. And the actuator says, oh, that's 50%, so it'll immediately go to 50%. Now remember, these are motorized, so they're slow. It might take 30 seconds to go from full close to full open, or it might take 90 seconds or 180 seconds. So what happens is this is going along, and you want 50%. It will take some time to get to 50%, but it will go exactly there. It won't dither getting there. This one might dither up and down getting there, but this one will not. It knows right where to go. And then if you say, I want 25%, it'll go right to 25%. That's what modulation is. Modulation is the preferred actuator if you're modulating actuators. And then we have fail-safe, which are spring return. And they're either two-position or modulating. Fail-safe, they can be modulating, all have spring returns. And so those are the type of actuators. Now, dampers have leakage class, and this is a little bit different than other control devices. So basically, if you say, now, these are some rules of thumb, and these are taken from some manufacturer's data. These are not exact, but close. So if you have, they use Class 1A as a maximum, okay, this is a AMCA, a maximum damper leakage per square foot. So if you have a Class 1A, which is CFM at foot squared for 1 inch of duct, it'd be 3. So the maximum damper leakage would be 3 CFM per square foot of damper at 1 inch. If you have Class 1 and it's at 2 inch duct, it's 5.66. If it's 4 inch pressure duct, it's 19.6 CFM per square foot of damper. Now you realize this is the class of damper, and this means what it is. So Class 1A through 3. Blade seals and jam seals change it slightly. And here's some torque loading classification type dampers. So if a damper actuated torque loading at 2 inches at 1,000, which is this one, 2,000 at 1,000 RPM, at parallel blade seals, this is the damper actuator torque loading. And this is important here because this is how you size an actuator. And that's what a control contractor needs to do, is put the correct actuator on the damper. We're talking electric actuators here, but if you have pneumatic actuators, it's slightly different because the pneumatic actuators are always fail-safe. They have a spring, right? So as they open, they're pushing against a spring, and when you stop it, then that spring will run it closed. Well, part of the problem is that if you have a whole, let's say if you put a small 45 inch-pound actuator on a class 4, which requires, it has 20 pounds of torque on it, and you put an actuator on that's smaller than that, then it can push open if it's pneumatic. Now, if it's electronic, it won't push open, but it might actually damage the actuator. So it's important that the torque loading, that you always select an actuator that has more torque than the service will have on it. So here's the type of classification: 2 inches with 1,000 foot. And here's the different inch pounds per square foot. Everything's per square foot of damper. And you will see that these parallel no edge seals, parallel with edge seals, OBD no edge seals, OBD with edge seals, round. So these give you the different dampers with edge seals, and this is how you select your actuator. So what you do is you find the actuator torque in pounds per square foot by multiplying the damper square feet by these torque ratings, whatever it is. And that's how you size your actuators. Standard, a maximum 2 inches, 1,000 foot. Medium is 3 inches, 2,500. High is 3,500. Extra high is 6,000 feet per minute. And of course, pressure drop in inches water gauge. If the duct velocity is 500 feet per minute, then a V groove is 0.011 or 0.009 if it's an airfoil blade. So these dampers I showed before, which had the little kink in them, those are V groove, they're called. And they're V groove because the V sits in the next damper, so that groove provides a seal basis for it. The V groove blades are airfoil blades. Size of damper in square feet, here's how you actually do it. Type of damper, air velocity and duct pressure at damper location. Type of actuator to be used. Select actuator torque loading value from table or from manufacturer's data, either one, so the manufacturer may have the data, or you can use this table. And of course, because these are kind of average rules of thumbs, always give yourself some shoulder. Don't size an actuator right on the torque. Mainly you may be off. They may decide to have a little higher velocity with a little higher pressure, or give yourself 20-30%. I would not size it right close. Multiply the value by the square feet of damper area. Select an actuator that has greater torque than the calculated torque. Here's an example. Given a 6.5 square foot OBD, low leak damper, and a 4-inch pressure duct at 2,800 feet per minute. Okay, so from the table, a 4-inch low leak. So here we are, 4-inch, and it is a OBD. So it's an OBD with edge seals, low leak. So it will be 10. So that will have a leak. OBD has a factor of 10. The area of the damper is 6.5. So we're going to take the torque is 6.5 times 10, which equals 65 pounds. So we'll select a 90-pound actuator, because here's your actuators up here. Here's a non-spring return. And you see you'll need to have a 65 pounds. So you could probably do a 90-pound for that one. A 90-pound actuator would suffice in both cases. So that would work, and that's how you size them. It's really kind of easy to size these. Now, I've seen some disasters in sizing them, especially with pneumatic. I've seen pneumatic actuation where the control contractor missized the actuator, and we had dampers that were it was in a clean space, and the damper was about 80 feet long, about 3 feet high on the lower part of a wall, and it was separating a fan room from a corridor room. And when we were at startup, the damper, we started a pole of fans. It was about 140,000, 200,000 CFM. I don't remember, but it was a whole bunch of main axial fans, had lots of horsepower, lots of power, and they started them up. And I was sitting in the space and watching the damper started fluttering. It started vibrating violently, and then it had enough force to overcome the actuators and slam shut and move the wall about a foot. So they had to tear that whole wall down and rebuild the wall. So it can be catastrophic, but it's only in unique circumstances. So try to do your damper actuators correctly. Duct pressure directly impacts damper strength to withstand close-off pressure. Higher the pressure, the heavier the gauge of metal that you use in the damper construction. Velocity pressure directly impacts the force required to close or open against velocity pressure. So here's kind of, now I'm going to give you this because I actually tried to calculate this before and I realized I'm not smart enough, and I'll show you why. So here you have air velocity against this damper blade, and so if you're doing a calculation, you would do it at 50% point, and 50% point of this damper is opening this way. This will be a force that helps it go that direction. This will be a force that's opposing. Now these forces will sort of look like they equal each other, but they don't equal each other when it's in vertical. As it starts to tilt, it doesn't equal each other. So the torque is the air velocity pressure times the moment arm. But what happens is an OBD starts going together. You can see that the air goes together and is forced into this jet. And so this has a moment torque this way, this has a moment torque this way. So the velocity pressure equals, that was 4,005. In this particular case, it'd be 2,800 times 4,000 squared equals 0.6991 inch water gauge. 6-inch dampers, 3 times 6699 equals 2.073 per square foot. And the 2093 times 4, because it's the size of this damper, it would be 8.39 inch pounds. And then times 65 the area, it would be 504 inch torque, 8.3 times too large. So that's a calculation that's totally wrong. It won't work. You need to use a table. And it just doesn't work. Don't try to calculate them that way. All manufacturers lab test their dampers for actual average torque numbers as shown on slide 8. Don't attempt to estimate the torque unless you are a math and physics whiz, because I don't really know what calculus you would use to use that varying torque against them. I'm sure it's possible. Smart people can do that. But for us, just use the table. All right, the last consideration is sound. All damper generate noise. Be aware that the NC noise values shown in this chart are average for general type of damper at various velocities. So here's the velocity, here's a V groove, and here's airfoil. And this is the NC values, and you can see at 4,000 feet per minute, V groove is a 60 NC, which is seriously loud. Now these are values inside the duct, but they're still very, very high, so you need to be careful of that. This noise inside the duct, which lessens to, in effect, in the space, because you got to have breakout noise of that duct, unless the damper is exposed to the grill, like behind a grill or at the end of a duct, then it won't be contained inside the duct, so it'll be exposed. So just remember that whenever you're doing dampers, noise may become an issue. So these are very, very high. This is room noise level, and this is very low, but these here are very, very high. Control actuator, submittal actuator catalog, or submittal sheet will provide the actual torque of the selected actuator. This is the actuator that will tell you what the torque is for the actuator. And that's all you need to know to be able to select an actuator for your calculated torque. This one's 180 pounds. Wiring diagrams may be separate technical data sheet, but they'll be there. So that was short and sweet. I hope that was somewhat helpful. Dampers are much, much easier than valves. So thanks for watching. I appreciate you watching these videos. Catch you on the next one. Have a great day. Thanks.